Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Simon Phillips, Chief Technology Officer at Oxford Quantum Circuits. Simon and I spoke about their unique approach to building quantum computers using superconductors, why their quantum computer is online just some of the time, his journey from gaming to quantum computing, and much more. I hope you enjoy this episode. Hello, Simon, and thanks for joining me today.
Hi there. No, it's a pleasure to be here.
So who are you and what do you do?
So I'm Simon. I'm the CTO, Chief Technology Officer at Oxford Quantum Circuits in the UK. And I've probably got one of the more exciting jobs in the world. So my role is to be entirely responsible for the technical output of Oxford Quantum Circuits. We're a quantum hardware company. We build quantum computers based on superconducting circuits. And my job really is to kind of set the goals and vision of the technology and then work with all of our internal technology teams to deliver against our roadmap. That kind of overlaps into the world of physics, the world of product development, the world of finance, and all of the things that we need to do as a company to make sure we can deliver the world's best quantum computers.
I agree with you that CTO is probably one of the best jobs out there.
It's cool, right?
You mentioned superconducting qubits. Now, I think other vendors are using superconducting for their quantum computers. Could you explain what makes Oxford Quantum different?
Yeah, absolutely. So we're based on superconducting circuits, and it's quite a popular modality, if you like, because of the engineering capabilities and some of the routes to long-term scaling of it. But at Oxford Quantum Circuits, we've got our core technology. It's called the Coaxmons, and this is what we span out of the University of Oxford with in 2017. And it's a 3D architecture for superconducting circuits. So it's completely 3D in so much that our control wires are completely out of plane. So we have like a really beautifully clean substrate with our qubits and resonators on, and all of the kind of control wiring and all of the bits that the qubits hate that bring interference and crosstalk, we've taken out of plane and they come in completely 3D, which gives us a number of really good advantages or less challenges to scaling than some of the other superconducting circuits.
Are these challenges just related to noise, or do you believe you'll be able to deliver, for instance, better connectivity or higher number of qubits sooner? Marketing spin.
So without getting too marketing spinny, what it really allows is, if you imagine taking away all that control wiring from the substrate of your chip, so there's no like through silicon vias or air bridges or bonding. The other really cool thing with the Coaxmon, we don't ever galvanically bond to the chip, so it sort of floats in space. And what that means is we're completely free to run any kind of connectivity patterns between the qubits without having to navigate any wires or re-architect anything. So it gives us a really clean, neat solution for trying some really exciting things. But ultimately what it means is there's less things to interfere with the qubits. And because we come straight down in 3D from kind of top to bottom in a capacitive coupling style, we have really low crosstalk between our qubits. So they're perfectly mode matched up and down. So as we scale the numbers of qubits, we're really not compounding crosstalk or other kind of errors. So whilst it's still, we're still noisy with bits, and we're all trying to work out the best and neatest way for doing error correction as we move towards being fault tolerant. But for sure, we start with a lot less challenges than other people, which gives us a lot more freedom for design.
And given that it's superconducting, you still need cooling, right? You still need cryogenic cooling or very, very low temperatures.
Yeah, that's right. So we run at millikelvin levels, as all superconductors do. But again, the really neat thing is, because of the 3D nature, as we add qubits to our processor, we sort of say linearly bigger, right? So we're adding like rows and columns of qubits, as opposed to getting exponentially physically bigger with 2D wiring or kind of bump bonding stacks and things like that. So even though we have cryogenic cooling, the physical space and the density of our processors means we can fit many more qubits in an off-the-shelf dilution refrigerator. So we're quite fortunate in that the largest dilution refrigerators you can buy off the shelf today, we can see really far into the future with that infrastructure. So it's one less thing to worry about, right? So
to the extent you can share, what is the stage of the company in terms of funding, number of people, working product? Where are you in the quantum journey?
Yeah, so we curiously still call ourselves a startup. I'm not quite sure when that changes, to be quite honest. I think back in the day, in a previous life, I used to make video games, and a startup really meant you're sat in a bedroom with your mate kind of coding video games. But we've just done a first close on our Series A. It was a £38 million round, which we're really proud of, and so the largest quantum Series A in the UK. That was pretty cool. We've also commercialized our current gen quantum computer, Lucy. It's an 8-qubit quantum computer, and we launched that over AWS Bracket back in February now, I think. And that was a real big milestone for the company to do our, the thing we want to do, which is accessibility, right? The more people that can use quantum computers, the better people can learn what they're doing, the barriers to entry come down for business value problems, and the whole ecosystem starts building. So we've launched our first quantum computer. We've just closed our Series A. As part of that, and this was public information as well, we've got a new co-lead investor that's going to help us internationalize the company. So we're starting to look at what we can do in other territories. We've got a Japanese co-lead investor, so that's really exciting for us to leverage talent in Japan and see what we can do with quantum computing there as well. And really now we're able to really take advantage of the Coaxmons core technology in terms of scaling. So we're going to see quite a quick increase in our qubit count, but more importantly than just qubits, in our quantum volume, our kind of error rates as well. So we want to focus on high quality processors rather than just chasing qubit numbers. But we should see now with this fundraise a real quick acceleration through the gears.
Let's dive a little bit deeper into the AWS, into the Bracket integration, because I'm curious about several aspects there. One thing I think I saw in the press release is that now AWS Bracket has a computer that's in Europe. If I'm an end user, why do I care where the quantum computer is?
Yeah. No, absolutely. So the AWS in Europe is our quantum computer, is Lucy, OQC's quantum computer, and it's important for a number of reasons actually. First and foremost, the real big drive at the moment is around data sovereignty or data onshoring. So if you're starting to look at building proprietary algorithms or applications, you want to make sure that you've got complete data traceability from where you start to where you finish. You really want to know where that computer's located. And that's been a really important requirement for a lot of people we've spoken to as well. So there was that kind of aspect of things. Next, at the moment, we live in a world today where we have uptime for quantum computers. We sort of run on Windows and not the operating system, as in the gaps of time. But we need to schedule those time to be friendly with academic research groups or businesses or things like that. Otherwise, we end up queuing. We're quite passionate about how we can move that forwards, really. There's a number of reasons why it's important. And going forwards in time, latency is going to be a real big issue as well. Today, it's not so much of a problem because we're only dealing with handfuls of qubits. But fast forward a few years where we've got hybrid applications running on CPUs, GPUs, and QPUs, you're really going to care about that kind of latency to where you're based and where the other technology is based. So that's primarily why it's important to be in Europe.
Regarding the uptime, is it why is it not up 24 hours a day? I mean, I know quantum computer is up 24 hours a day, but you have to tweak the qubits in between operations. You have to clean things up. Are you making changes to the machine as we go? What's the reason?
So there's a number of things that thread into it. I mean, probably So at the moment, we live in a world where we're constantly calibrating the computer. We're really learning about what drift means for us and how we can constantly keep the results better. And bearing in mind, we build the whole back-end stack, right? From fabricating qubits, we build our own room temperature control electronics. We've got our own software stack with compilers and optimizers. So we're constantly able to squeeze more performance and power out of the same hardware just by keeping the thing well calibrated or up to the latest firmware designs and things like that. So we are constantly tinkering with it, but you're right to say it's on 24/7, right? The cryogenics are always on, the qubits are always there. The uptime at the moment is really based around the way the partnerships are forming with people like AWS, in that they want, and rightly so, really good SLAs for customers. So if you're going to run something on our computer over AWS Bracket, you need a certain level of some certain level of service level agreement where that if you've got a problem, it can be solved on time. If you hit a problem with a quantum computer, we have someone on it within 15 minutes to solve that problem. But what that really means is we end up narrowing down to an intense window of operation. But our vision for quantum computing really is one of seamlessness in the future, right? So we see a world where, much like today, you can almost take for granted that if you want 1,000 GPUs on your network, you can just provision it with your local provider, or if you want more storage, or if you want more compute power, you can just add it to a menu and it's on your network within seconds. And that's where we see quantum computing going. So we're talking about always on, always calibrated, always available resources. We've got a long way to go, of course, before this is realized, but really we want to move away from this kind of uptime and Windows to just being able to spin up a QPU like you would do anything else. That's the goal.
If I'm an AWS Braket customer, I could run it on Lucy. I could probably run it, I think, on Rigetti or IonQ or a number of other vendors. And let's say that I find your technology very cool, but I just care about the results as a customer. Why would I choose Lucy over other computers that I could use on AWS Braket?
Yeah, I mean that's a great question, and we fully embrace the ability on Braket. One nice thing is you can write your code in Braket, and you can just swap out the ARN at the top, right? So you can jump from Rigetti to OQC, and I think that's really cool. I think for us, what's important is that we've got high quality processors, so longer coherence times with good 1Q and 2 qubit fidelity. So we like to think that the results you get from Lucy are going to be really high quality. That's one thing that's really important. And one thing we're super keen to do is really support the community in understanding those results as well, right? So we have a lot of ways of being able to communicate via AWS Braket, whereby if you want to understand your results a bit better, you can get in touch. We can make postings and really understand how to write code for quantum computers. And I think that's a really important point there when we think, we have to acknowledge that today the computers aren't useful for business value problems. Today it's about learning how to use them and learning how to think about how to develop quantum algorithms or quantum code. And it's great to be able to do it at a level where you can write some assembly language for 8 qubits and really read it, right? You can understand the code, you can understand the results, and you can start mapping that to your learning process. And as the processes get more complicated, you're actually going to lose that ability to fully understand what's going on. So we encourage people to look at the results, reach out to us about what they mean, and we really help you understand what it is to write code for our processors.
Some companies believe in vertical integration, that the software should be really tightly coupled to the hardware to take maximum advantage of it. Whereas, as you described, you're in AWS, I could change a couple of lines in my quantum code and run it on yours versus someone else. How important to you is that coupling between software and hardware, the optimization of the software to take maximum advantage of the hardware and overcome its limitations?
Yes, I think that goes up and down the stack a little bit in different ways. So we certainly believe that when it comes to the control of the qubits itself. This is why we started a program 3 or 4 years ago to build our own control electronics for our computers. So we have a team of people dedicated to PCB design, FPGA design, and actually tuning the control hardware to the topology of the process itself. So as we move into error detection, error correction, and things like that, we've got really high throughput of information. So when you run a task, it's going to run in lightning time. We can then do, all the kind of things we need to do to build our error correction without, having to buy off-the-shelf hardware. It's all custom designed. So we believe that needs to be really tightly coupled. We then, and I guess most people do this, we have our own compiler, which will take advantage of the nature of the processor itself. So you can write some more generic code, and our compiler and optimizers will actually map that to the processor in the most efficient way. That's great for getting good results. It doesn't always help learning, though. Sometimes you want to just run it verbatim, right? You want to say, run on qubit 01. I just need to see how these qubits are going to operate. So we offer that kind of flexibility. But I think really we want to get to a world where above that, in the application space and the algorithm space, that you can start using whatever tools suit the person or the problem better, and then let the rest of the stack, so some of our software through to our hardware, do the tight coupling for performance.
Can you give us a little peek into your technical roadmap? What do you expect Oxford Quantum to offer in the next year or couple of years? Is it just more qubits, or is it something else?
There's a multitude of things. I think there's always going to be more qubits, but like I said, I think what we really want to do is not necessarily focus on the number of qubits. We've actually built our roadmap to do with target error rates, and I can't go into the specifics of what they are, but we really feel that there's a number of qubits to a point, but then the more important factor comes into the fidelities and the error rates that we're able to achieve, and we map that against algorithms and business use cases from there. But I think we can really think about our roadmap probably in three different strands. We've got the main technical strand, the processor power. That's one thing. Then we've got what we call kind of customer on ramp, and this falls firmly into the technical space as well. Is to how can we get end users to write code for the quantum computer that starts solving their problems. So it might be specific features that they need, it might be specific languages that they want us to ingest, or it might be, a number of combinations of those things. But really, we need to help enable large businesses build out the teams of people to develop their algorithms that will be proprietary to them. So we've got a big strand there. And then the third piece from us is infrastructure. We need to make sure that when the processors are capable enough and the customers know how to build their quantum algorithms, that the computers are where they need them to be in terms of data sovereignty and connectivity and hybridization and all those things. So we're going to see some quite exciting things in all three of those strands from OQC, both processor capability, customer interactions and customer on-ramping, and infrastructure as well.
People get into quantum computing from different areas. And I don't remember if I heard about anyone else who came to quantum computing from gaming. How did that teleportation process happen?
Yeah, so it's a real interesting one, actually. So yeah, I started in the video games industry when I was, I don't know, quite young, in the 90s, let's just say. So and actually one of the things I did enjoy there, as I said earlier, was I used to be an assembly programmer. So just being able to read assembly language and know what it's doing at a hardware level is really fascinating. I'm quite enjoying looking at Chasm codes now. And really that journey for me was one of enjoying technology and one of enjoying business and entrepreneurship. And, we did some really good things in the video games industry in terms of growing businesses, and real cutting edge stuff, maybe not in the same way that deep technology is, but, we experienced when 3D graphics first came out and when free-to-play business models first came out, when the internet first came out, and all these big firsts that were like, wow, we have no idea what's coming next. We just have to architect the future, right? And I see a lot of similarities in quantum today whereby, no one really knows how this business is going to evolve or how the business model is going to evolve. And it's so exciting to start shaping that. But yeah, I've always loved technology. I kind of have a bit of a cheesy one-liner that a lot of our current investors would have heard me say in a pitch, and that I thought I could change the world with video games, but really we needed quantum computers to do that. So fortunately for me, Alana kind of really brought into my passion for technology and my passion for just enabling teams and inspiring teams of experts. So I'm really fortunate that all of our leads that we have a number of technology teams within OQC, and they've been set up in a very specific way to enable all the leads to have full ownership of their space. And these are, world experts in quantum or in, decoherence or in fabrication and things like that. So my job really is just to enable them to think big and enable them to have the resources they need to do things. And that's everything I learned in the video games industry. But yeah, for sure, I'm in a real fortunate position at the moment.
As we get close to the end of our conversation, I'm curious, what can you tell me about the UK quantum ecosystem, and maybe if you know how it compares to, say, France or Germany or other European countries?
Yeah, so actually, I think North America aside, which has got a pretty good ecosystem, I've seen it change a lot, even in the last 2 or 3 years. I think 3 or 4 years ago, you'd kind of say you're in quantum, and people would look at you like you've just walked off a spaceship. Whereas now, actually, I think we've grown from, I think I was employee number 4 or 5 or something like that, and we're now in 65 people. I think we have today, and it's actually only now we're starting to see people that have experience in industry of quantum. Right? A few years ago, it was either you've got a PhD or we're bringing you from a different field entirely, and we're upskilling you to do something. And yeah, really, it's only now that this ecosystem's got to a point where there is experience there, and that's fantastic. That's the only way this whole technology is going to thrive. And we're starting to see that in other areas. I think UK feels relatively advanced. I mean, Europe's great from a financial point of view. They seem to be able to get a lot more European money into businesses there that we're not jealous of at all now. But so it's definitely growing up. It's definitely growing fast. And part of our goals, again, is to help stimulate that ecosystem. I think the bigger that is, the easier we can all find people, we can find connections, we can be ready for quantum.
And Simon, how can people get in touch with you to learn more about your work?
So I'm more than happy for people to drop me an email. I love chatting about technology. I love chatting about science. I love chatting about quantum interaction. So people can reach out to me. I'm on Simon at oxfordquantumcircuits.com. It's a bit of a mouthful, that URL, but yeah, just Simon at oxfordquantumcircuits.com, and I'm more than happy to kind of have chats.
Well, it's been wonderful chatting with you today. Thanks so much for joining me.
Brilliant. Thanks for inviting me. It's always good fun.